Hello everyone, I'm happy to share our work here. We propose a new vision and language task named REVERIE. We humans have a long-haul goal, namely to build intelligent robots that can perceive the environment, execute commands, and communicate with humans. Toward this goal, several related tasks have been proposed, such as visual question answering, image capturing, reference expression grounding, and the most recent task, vision and language navigation. However, they cannot reflect one of the most appealing applications of robots, namely communication about remote objects. For example, we may ask a robot to bring me the blue cushion from the living room. In the hope to drive progress in this field, we propose a new task, REVERIE. Here is a demo of the REVERIE task. In a real-world image rendered 3D simulator, a robot agent is initialized at a random location. Then it's given a natural language instruction referring to a remote object. The agent must navigate to an appropriate location and identify the target. The agent can look up, look down, and look around at each step. The blue cylinders indicate nearby navigable viewpoints provided by the simulator. The REVERIE task involves both room-to-room navigation and referring expression grounding, but it has several key differences from these tasks. Compared to the room-to-room task, REVERIE differs in two aspects. First, REVERIE uses concise, high-level instruction, such as the first bedroom on level 2, while the room-to-room task uses detailed, low-level instructions, such as go to the top of the stairs, and then turn left and walk along the hallway. Second, the goal of the REVERIE task is to locate a remote object. In contrast, the room-to-room task aims to navigate to a remote room. Compared to reference expression grounding, there are three key differences. First, the target object is not visible at the starting location in the REVERIE task, while the target is directly visible in the referring expression task. Second, there is only one candidate image that contains the target object in referring expression, but in REVERIE, each panoramic image of every past location may contain the target. Third, the target usually appears in a front view in the referring expression task, but in the REVERIE task, the target may appear in various views as the robot can change its pose to observe the environment. Okay, let's move to our dataset. The dataset consists of about 21,000 instructions, using a vocabulary of about 1,600 words. It involves 4,000 target objects, falling into about 500 categories. The dataset is divided into 4 splits, using the same strategy as the room-to-room task. This means you can address the REVERIE task with the help of instructions from the room-to-room dataset. Here is a comparison with related datasets. In summary, the REVERIE dataset is featured in high-level, human-annotated, unambiguous instructions and object bounding box in dynamic real-world image rendered environment for remote object grounding. Okay, then what's the challenge of this task? There are 3 main challenges. First, the appearance varies greatly, even for the same object, in terms of shape, scale, or aspect ratio, caused by different robot pose. Second, the instruction structure is complicated, involving various linguistic phenomena such as downgrading modifiers, spatial relations, and imperatives. Third, it's difficult to understand the instructions. On one hand, the instructions are very short. On average, it's 11 words less than those of the room-to-room dataset. On the other hand, about 56 instructions mention 3 or more objects, falling into nearly 500 categories. To solve this task, here we propose and test several baselines. As the REVERIE task involves both navigation and referring expression grounding, so an intuitive solution is to combine state-of-the-art navigation and VARIE grounding models. We totally test 8 navigation methods and 3 referring expression grounding methods. There are 2 ways to combine them together. The first one is to perform object grounding when a navigation ends. The second one is to perform grounding at each navigation step. To reduce the number of combinations, we use the best object grounding method for the first kind of combination. This reduces the combination number from 24 to 8. We find out the best grounding method by assuming the robot agent have arrived at the target room and just perform object grounding. Results show that MATNet performs best. Once we have evaluated results of the first kind of combination, we can further reduce the combination number to 1 for the second combination manner by just using the best pointer and navigator. We implement this kind of combination by an interactive navigator pointer model. Before diving into our interactive model, let's have a look at how a general navigator works. A navigator takes in 2 kinds of input. One is the language instruction, and the other one is observed panoramic image. For convenience, the panoramic image is usually divided into a series of discrete images. A navigable location is represented by such discrete images and its orientation to the robot's front direction. According to this information, navigator selects one candidate as the navigation prediction. Our interactive navigator pointer model consists of 3 components: a pointer, a navigator, and an interaction module. At each step, we first use the pointer to predict the most matched 3 objects in each navigable view. The labels and VARIE features of these 3 objects are used as the input of the interaction module for further encoding. These encoded object features are concatenated with the whole image's feature. Then the navigator encodes this concatenated feature with reference to its memories. At the same time, navigator also encodes the instruction. This information are assembled to generate new memory, and to predict confidence of this candidate view to be the next navigating action. Repeat these steps for each navigable location, and select the view with the highest confidence as the final navigation action. That's how our model works. Now let's have a look at the evaluation metrics. A task is considered successful if it selects the correct objects from a list of candidates. All the predicted bounding box has an IOU no smaller than 0.5 with the ground truth. Then the performance of a model is mainly measured by remote grounding success rate, and the success rate weighted by path length. We also measure the navigation performance with 4 kinds of metrics. Please note, in our task, a navigation is considered a success if it stops at a location within 3 meters to the target object. Here are the results. The first 4 lines are obtained by using baseline navigation methods. The following 4 lines are obtained by using state-of-the-art navigation methods. For these 8 tests, we perform object grounding when navigation stops. Results of our method is obtained by the interactive navigator point model, which performs object grounding at each step of the navigation. And the last line is human performance. The random agent only achieves RGS around 1%, indicating the REVERIE task has a very large solution space. The shortest model assumes it has arrived at the target room and just performs object grounding. It shows that the grounding success rate is about 15%. The basic room-to-room models only achieve success rate around 2%. Among state-of-the-art methods, fast short performs best, but with only 7% success rate on the test split. To test the dataset whether it has a bias on instructions or images, we evaluate a variant of fast short, which only uses instruction as input. It shows a significant drop, especially on the value-scene split, indicating both language and visual perceptions are important to our task. Finally, our interactive model achieves the best performance among all the evaluated methods, indicating the interaction between navigator and pointer is helpful. But this result is still far behind human performance on the test splits, leaving an extremely large space for us to explore. Here are the codes and dataset for our REVERIE task. Thanks for your attention.